Right, so hello everyone, thank you for coming. My name is Tanner. I'm a former launch school student, and today I'm going to be talking about first, distributed systems and the general challenges in architecture involved, as well as decentralized systems, which are a subclass of distributed systems, and finally, the applications of blockchain in a decentralized system. And blockchain is really just a solution for a very specific problem that arises in some decentralized systems. So it's not a universal solution, and it has very specific use cases, and it's not always appropriate. And my hope is that by the end of this talk, why blockchain is applied and when it's most useful will be apparent. So, all right, let's get started. First, we have to define our terms, and this will allow us to be more precise when analyzing distributed systems. So the first term is a service, and for the sake of this presentation, a service is the primary function or set of functions that end users gain access to by using a particular piece of software. Resources are those things that are necessary for the service to be initially and then continuously provided to the end users. And the provider is just the entity or group of entities responsible for ensuring that those resources maintain operational. An example would be Google Drive. The service there is the productivity suite. The resources are the hardware, the servers, the data storage centers, as well as the manpower. And then the provider is obviously the corporation that is Google. So in architectural distribution, sorry, that's phone's being called. In architectural distribution, the servers or resources are distributed in the back end, but to the client, the service appears as a single service. So that's called distribution transparency. And in architectural distribution, companies tend to introduce this sort of architecture for a few reasons. First would be to scalability. At some point, the service you're providing is going to have too large a user base, too much demand for single pieces of hardware to handle it. So you probably have built applications before using Sinatra or Ruby on Rails or some other framework that used a single database, single web server, and then serves the front end. Now, that's useful for minimum viable products and prototyping, whatnot, and even small to medium-sized applications. But when they grow, that's no longer possible, feasible, or effective. So, for example, if you are a social media site, the amount of user data you're storing will be too large to store on a single database. At that point, what you can do is something called vertical scaling or scaling up, which means you upgrade the hardware itself. So to handle this situation, you would purchase better storage devices. And ideally, what would happen is that if you spend twice as much money on a storage device, you'll get twice as much storage capacity. But actually what happens is that the more expensive the product, the returns start to diminish. So maybe the first time I scale up, the servers are able to store twice as much when I spend twice as much. But if I double the price again, I might only get a quarter more storage, at which point it's time to scale out. Other reasons to distribute your backend architecture would be if you're trying to optimize for certain types of queries. So, for example, if I was a online magazine service, then I would get a lot of read queries. What I would do in that case is have a lot of distribute my databases so that to serve only read queries. And that allows each server to have to process less read queries per second, meaning they can respond to those queries more quickly. Basically, this is called read scaling. And then the final primary reason to distribute your backend would be fault tolerance, especially for data storage companies where the access to the data and durability of the service is really important. The fact is you need backups, and backups are only safe if the devices storing the backups and the devices responsible for serving the content are independent. And so that's just simple data replication. So even in distributed systems, traditional distributed systems, the control over the distributed system is still centralized. So you have all these different servers and resources, but they're still controlled by a single company or corporation. And once again, Facebook is a good example of this. And there are problems with this, namely security, privacy, and anonymity. When we store our data with these centralized providers, we trust them to be good stewards of that data. We trust them to keep it secure from malicious forces. We trust them to keep it private, both from internal employees as well as third parties. Trust them certainly not to sell our data. And then some people, but not all people, have anonymity as a value, which is much more attainable in decentralized systems as well. So those are the reasons we would want to decentralize a system, or as end users, we would want to be using a decentralized system. And as providers, we would want to be building a decentralized system to cater to end users who have those values. Now, decentralized system versus centralized system is just something like this. A very simple example is on the left, you see that there are 3 end users all communicating directly with each other. And each of these end users is actually also a provider. So no single provider on the network is responsible for providing all the resources, but they distribute the burden of providing those resources, similar to how someone might have multiple databases in the back end, all distributing the burden of data storage. The difference is that a single company or entity does not control each of the providers in a decentralized system. These are all end users, and they are all independent of each other. It's a single service, but many independent providers. The term independent is important here. Whereas on the right, this is just another example of a distributed system where all those resources are controlled by that single entity. And so we can really think of decentralization as, at least for this presentation, as a distributed architecture alongside distributed control of resources. So it's that combination that makes it decentralized. And peer-to-peer systems are exactly this. Some interesting and notable properties of peer-to-peer systems is role symmetry. So think about BitTorrent, where if you download the BitTorrent client, you can then download torrent files from other peers on the network, and you can also start seeding or providing those torrent files to other people who are trying to download them. So you're both a provider contributing a small portion of your computer's computation power and data storage to the overall service, and in return you also get to use the service. Another interesting property is the heterogeneity of resources, meaning storage, computation, routing, and business logic. And that's important because in traditional distributed systems, think Facebook or Google, they of course have distributed backends and data centers all around the world. But the fact is that the proprietary technology and hardware resources used are pretty similar across all these different data centers. And research has shown that similar resources, even though they're distributed, have correlated failures, which means that even though they're independent, failures correlate. So if they're using the same type of database as backup servers as they are as the primary servers, then that type of, that there's a higher probability that the backups themselves fail in combination with the primary servers. Another important property of peer-to-peer systems is something called high churn. And basically what that means is that the network is very dynamic and constantly changing in its topology. New peers are joining and leaving the network all the time. And so this is actually a huge challenge that peer-to-peer systems have to deal with, because as opposed to a traditional distributed system where all of your resources are dedicated, you can be pretty sure that they're going to be online most of the time. You can't be sure of that in a peer-to-peer or decentralized system. And then of course there's the distributed sourcing of resources, which is pretty much implicit. So there are some challenges associated with distributed systems and even more associated with decentralized systems. Like I said, decentralized systems are a subclass of distributed systems. So all challenges in distributed systems exist in decentralized ones, but then even further. So they're even harder to build properly. So first is, of course, the protocol you're going to use to distribute the data. What kind of design pattern are you going to use? Are you going to use just leader, single leader, multi-leader, leaderless, like Cassandra? If you've ever heard of Cassandra, that's a leaderless replications protocol. Another huge challenge is latency. Basically, if you have distributed resources, the fact is that when the different providers or peers have to communicate with each other, that communication isn't instant. This is a problem in traditional distributed systems as well. Think about a social media site that has 3 different data centers, all serving read requests and one serving write request, okay? So when a user posts a comment, it sends that write request to the server handling write requests. Then that server that processed the write broadcasts to the other 2 servers, hey, I just received a write. This is what was written to the database. Now I'm replicating it to both of you. Now, while that replication process is happening, the same user who posted the comment refreshes their page, and they get randomly routed to one of the other databases when they're also supposed to be replicas, but this database has not yet received that latest update. So it appears to them that their comment disappeared. This is a really fundamental problem that has to be solved in distributed systems, and it's just one example of how latency can affect the quality of a service, and this exists in both peer-to-peer systems and regular distributed systems. There's of course the fact that you have to handle node failures, especially in peer-to-peer systems where the majority of users are going to be using general purpose computing devices, like laptops, desktops that people turn off and on all the time. They're not trained maintainers necessarily of that device, so that's also contributes to the higher churn. And then there's finally the fact that in peer-to-peer systems specifically, it's built into the very core of the service that the people who are providing part of their computation power towards the common goal of the service are not always trusted. Some peers are assumed to be untrustworthy, and if you've heard of the term Byzantine fault tolerance, which is a specific type of fault tolerance we'll talk about later, referring to Byzantine nodes. Some people pronounce it Byzantine. That a Byzantine node is just a node that is considered a bad actor, one trying to purposely hurt the system. Finally, in distributed systems and especially decentralized systems, there's a problem of agreement or consensus. The fact that data is distributed and it's not necessarily the case that the entirety of the data is replicated on each node, plus the fact that there's latency. So you can have some nodes who have out-of-date data and divergent data, plus the fact that you have untrusted peers who might try to modify the data in ways that is just to create inaccuracy in the system. It means it's very hard to come to a consensus on what is globally true across the entire system. Every node has their own version of truth. And this is kind of talking about this in the abstract. It's hard to see necessarily what kinds of services one would need this global source of truth to be important. And so that's why we'll take a look at a tangible example, which is eCash. So this is the concept of digital cash, which is different from banking. So how we use cash in the real world is if you want to give cash to someone, you simply take it from your wallet and then you give it to them. And then they can go purchase something with it or deposit it. But there's no record that you gave that person cash. The reason is because it's just direct communication. When we try to pay digitally, say through point of sale or virtual checks, that type of thing, it's not the same as electronic cash. What we're doing in cases like that is we're relying on some sort of centralized authority to validate that transaction and then communicate with the central authority that's in charge of validating the recipient's transactions. So eCash directly is a lot different, and it's also a problem. And the reason is because in the real world, you can't double spend your cash. That's because the value, the thing that represents the value is physical. In electronic cash, it's just pure information. And so if everyone had their personal, like, quote unquote, electronic wallets, they could simply put more information in it that says, oh no, I have more money. They could spend the same money over and over again, create an infinite amount. So this is a problem. We need a way to globally ensure that cash isn't just appearing out of thin air and people aren't spending the same money twice. And this is one use case for a global source of truth where everyone can agree, despite there not being some centralized provider like a bank that's monitoring this for everyone. And that's actually the thing that Bitcoin came around to solve. And when I get into blockchain, it's basically going to be a simplified version of the blockchain that Bitcoin's powered by. Well, I forgot to mention, if you have any questions, just put them in the Q&A and I'll answer them at the end. So yeah, so this, like I said, this double spend problem is generalized to a consensus problem. So every node on the network can just claim that their truth is the global truth, and no one knows whose data is correct or accurate. And just breaking this down a little more, this is a problem because each node can change their own data however they want, and other nodes are unable to detect whose data is correct or if their own is. There's no central authorities or arbiters to determine this state is true or that state is true. So what do we do about this? Is there some sort of data structure that prevents people from corrupting it? Is this data structure something that prevents people from mutating it and going undetected? So any mutations would be immediately detected and people would know not to trust that data. And perhaps this data structure also allows, or rather empowers people to add accurate data to it and even rewards them for doing so, but makes it very costly and expensive to add inaccurate data. And of course, the data structure I'm talking about is blockchain. In the Bitcoin blockchain network, every peer, or every full node, there are different types of nodes, but for simplicity's sake, we're just going to assume that every node has a full copy of the entire blockchain. So it's just 100% replication. Every peer on the network, or node, Bitcoin node on the network, and from here on I'm just going to refer to it as blockchain nodes since the system I'm talking about is simpler than Bitcoin's actual implementation, knows the rules that the data must follow. In other words, when a blockchain node receives new information, it knows how to verify that information. And all nodes verify incoming information. Once they verify the incoming information, they'll either forward it to their neighbors or they'll simply drop the information if it fails validation. And this produces something called emergent consensus, which basically means that at one point or another, all nodes in the network will reach some state of full consensus, although that might not be instantaneous. And finally, blockchain allows this data that they're receiving and transmitting to other nodes to be easily verifiable, so it's quick and it doesn't use a lot of CPU or electricity, but very difficult to fabricate. Use a lot of CPU, a lot of electricity. It costs real money, and a lot of it, to try to fake data into the blockchain. So that's an incentive scheme that promotes good behavior, which is important when you can't trust people. If you can't trust people to follow the rules simply for the sake of following the rules, perhaps rewarding good behavior with money is the way to go. And that's kind of why, one reason why Bitcoin was so revolutionary is because it represented this very interesting intersection between economics, human psychology, and technology. And a fundamental idea in computer science is that, well, best demonstrated by the question, which is more fundamental, data structures or algorithms? And the answer is data structures, and that's because an algorithm is entirely informed and made possible by the structure of the data that it's operating on. So the question becomes, what type of algorithms does the specific data structure that is the blockchain make possible? And what is a blockchain anyway? Well, simply put, a blockchain is an immutable, append-only, replicated list. It's a very simple database, basically. And it's immutable because each element in the blockchain has some sort of special reference to the previous blocks, such that changing any of them changing any single element in the list invalidates the entire list. That's only semi-accurate, but for now, that's the best way to explain it, and you'll see in detail, more in detail later. And then it's only append-only because blocks cannot be added to the center of the list. They can't be added to the beginning. It's basically this massive growing list that only gets bigger by new additions being added to the end of it. And for those of you who are familiar with linked lists, you can think of a blockchain like a linked list with special properties. So just for those of you who are not familiar with linked lists, it's an elementary data structure where instead of an array where you have just a contiguous collection of elements, a linked list has specific elements that store references in memory to the next element in this quote-unquote list. So they don't have to be, so when you're storing an array in memory, you have to set aside a contiguous amount of space for it, of side-by-side cells. In a linked list, you don't, because you're simply storing references. And some properties of linked lists are that deletion, instead of removing an element from memory in linked lists, all you do is you dereference. So you can see here that node 1 references node 2, which then references node 3. If I wanted to delete node 2, all I would do is make node 1 reference node 3, and then node 2 is no longer relevant. However, you can easily add nodes to the beginning or end of the list, and therefore it isn't immutable because there's no way to also verify what type of data is allowed or isn't allowed. All that matters is that there are references in memory pointing to other nodes. But there are some important similarities between linked lists and blockchain. So this right here is just simplistic representation of a segment cut out of a blockchain. A blockchain has hundreds of thousands of different blocks in it. So this is kind of zooming in. And there are more properties on a production blockchain, but this represents the important ones. Notice that if you look at the block all the way on the right, it's got 4 properties: previous block hash, something called a nonce, which is basically a cryptographic helper, which we'll look at in a little more depth later, the data that the block is actually storing, and then this particular block's ID. So if you look at the middle block, you'll notice that its ID is ZFA, which demonstrates that the block on the right is referencing the middle one. And then its previous block hash is XYZ, which is the same as the ID of the block on the way right. So in that way, each block references the block preceding it. And how is the ID of each block determined? Well, it's determined by taking the hash of the data inside the block plus the addition of the previous block's ID. In this way, the ID of each block is intimately tied to the content of the block as well as the content of the previous block. And that'll make way more sense in a second when we talk about block validation. So if a new block comes into a node, it needs to be validated by that node before it's added to that node's local copy for blockchain. Remember that each node stores its local copy of the entire replication of the blockchain. And the way that works is, first, when a new block comes in, it'll look at the previous block hash, and it will see if it can find that previous block hash in its local copy of the chain, of the blockchain. If it can't find that, then it's considered an orphan block. And basically that means it's set aside until more blocks come in, and then it'll continuously check for that previous block hash that matches the orphan block. But that's just an aside. If it does find the previous block with the same ID, so if this was the block that came in and the previous block hash is ZFA, it would look for the block with the ID ZFA. If it found it, what it would then do is take the hash of this new block, the new block's data, plus the nonce, plus the previous block ID, and it would check if all of that equals this new block's ID, which means that which means basically that the data hasn't been mutated in a way that's not allowed. And then it'll validate all the transactions. So each block in the blockchain is basically storing an entire collection of transactions that need to be processed. And that's what this data element would store here. And finally, if it passed all those tests, then it would add the data to the block, it would add the new block to the blockchain, and then broadcast that new block to all its neighbors. But the problem is that still the blockchain, as I've currently described it, is mutable to an extent. If you change a block in the middle, you'll actually only have to change all blocks following the block you change, which means that if you don't, half the blockchain is immutable. Half the blockchain is invalid just by changing one of the blocks. But it'd be pretty easy to store the last block. To change the last block because it doesn't invalidate any subsequent blocks because there are none. And just to demonstrate what this looks like, if I wanted to change this block here, so say I wanted to change the nonce to 825. Now the hash of the previous block hash plus the new nonce of 825 plus the data would generate a new ID. So I would need to change this ID. Since I changed this ID, I then have to go to the next block and change it to the new ID. But since now this data has been changed, this ID is no longer accurate. And that's what would go on until you hit the end of the chain. And although that allows for easy detection, it doesn't take many hashing routines to perform that. We need to make it harder to mutate data, and that's where proof of work comes in, which I'm sure you've heard of if you've read about blockchain. Basically, proof of work is this concept of putting in work in order to submit a block. And not all nodes on the network, in a blockchain network, create and submit new blocks. Only miners do. That's what mining the blockchain means. It's creating these new blocks by collecting a pool of transactions, aggregating them together, and then submitting them as that single unit. And the way proof of work works is, if you recall so let's go back to the initial calculate ID function, which looked like that. It's just taking the hash value of this data, right? But with proof of work, what happens is that there's something called a difficulty, which is basically a threshold, a numeric threshold that the output of the hashing function must not exceed. So in that case, a lower difficulty means that there are less values that will satisfy that criterion, which means that it's harder to create a hash value that satisfies that criterion. The nonce is important. Remember, the nonce is just that, I said it was something like a cryptographic helper. The nonce is passed into the hashing function, and if the resultant hash does not satisfy the difficulty, then usually what will happen is the node trying to mine the block will increment the nonce by 1. And that'll happen over and over again until a hash value is generated that satisfies the difficulty. And nodes currently mining on, say, the Bitcoin network are executing like quadrillions of these hash functions over and over again in order to generate a block. And this consumes a huge amount of electricity. That's why specialized computers exist. And the reason this helps prevent bad data from making it onto the network is that, let me see, how do I describe this? The amount that it costs to submit a block is so great that if you submit a block that you know is going to be rejected, it's just economically not worth it. It makes no sense. And there's also a reward for submitting a good block. So when a node is initially mining, it creates an empty block. It collects those transactions from the pool of transactions, but it also creates an initial transaction to itself. And the amount that that transaction is for is based on a variety of rules that we don't have to get into. But basically, if their block is the one that gets submitted, then they get paid. And that's also how new Bitcoin is produced, because that's related to a mathematical formula. But once again, that's this economic incentive involved that prevents people from generating bad data. And like I said, it's extremely intensive and not cost effective to create an invalid block. But it's extremely simple to check if a block is valid, and that's because all it takes is what I showed before, just passing a few values into a single hashing function and running that hashing function once. Whereas generating the block with the correct ID requires, well, millions, billions of iterations of this hashing function. And so just an overview of this, the blockchain data structure alone is not what creates these phenomena. It's the combination of the blockchain data structure plus how it's used. Blockchain data structure is fault tolerant because it's costly to cheat, but it's beneficial to be honest. And the way that consensus is ultimately reached is that the chain with the highest amount of work is accepted, and invalid. So the chain with the highest amount of work is accepted, but invalid blocks are discarded. And like I said, every single block is independently validated by nodes that are receiving it, which leads to independent verifiability. Blocks are linked using the hash values, and these are very easy to verify, but they're extremely hard to manufacture. And each node that receives a block makes sure its proof of work was correct and verifies its transaction set. That's something I haven't really talked about yet, is the transaction set. So if we go back here, when I talk about data, like I said, that's a list of transactions. Well, transactions have to follow a variety of rules. And when a new block is received, not only is the block validated, but all the transactions in the transaction set are also validated. And what this basically does is, or what the blockchain really does, is just a historical record of how currency has moved around. And so by having the blockchain on a local copy of it, you can iterate through those blocks and the transactions and know how much money someone is supposed to have. And you can catch if a new transaction is trying to send money from a sender who doesn't have that money, you'll be able to see it because that data is available for you. And if that does happen, you'll know that that's an invalid block because the block's transaction set includes an invalid transaction. And finally, because this is fully replicated, that also contributes to not only fault tolerance and helps aid with high churn. Like I said, nodes are coming and leaving the network all the time, so the fact that it's 100% replicated and fully replicated across all nodes means that nodes leaving doesn't pose much of a problem to the integrity of the data, but it also means that all nodes are capable of verifying that the data is correct. Okay, that's my last slide. I actually expect that to go longer, but maybe I was talking too quickly. I don't know. But are there any questions? I'm trying to open the question. Okay. So no questions at the time. So I will hand it back over and allow the broadcast to be closed.